When we look around us in the world, we see matter in an infinite variety of different forms. You get solids and liquids and the gas like the air, and they have different colors. You have flames and sparks, and stars and rocks, and they have all these different forms of matter. This enormous variety is very puzzling to human beings. The scientists have tried from the beginning to try to see if all this great variety could really be representing different aspects, if in some sense nearly the same thing. We have now found out that the enormous variety of things can be understood if they were all made out of atoms. And these atoms don't have such a great variety of different kinds. They're just approximately, at first it was believed, about 92 atoms. And the atoms themselves were put in some kind of table of different kinds, and in the different combinations of the different forms of chemical combinations of relations, mixtures of the different kinds of these 92 atoms, we could get all the variety of substances and phenomena and so forth that we see. We have to add a few items to the atoms in order to understand everything. We have to add light, which was understood, and electrical and magnetic effects. And the light and the electric and magnetic effects were understood as being different aspects of the same thing, which we call the electromagnetic field, the very thing which is carrying the waves by which a radio transmission is able to carry my voice to you. Now, the next question was whether the pattern that was seen in the atoms by Mendeleev, for example, the relations chemically of one atom to another, could be again understood. And it turned out that the atoms could be understood if they were made of a small nucleus which is surrounded by electrons. And the different atoms of the different kinds were all represented by different numbers of electrons. Carbon has 6 electrons, oxygen has 8 electrons, and so on. So this is of 2 steps in a long task to try to represent the different varieties by single things, to look deeper and deeper into matter and to find out what it is. And what I want to report to you tonight is how we're making out in this attempt to understand variety in terms of simple numbers of elements. And you'll see that the story is an interesting one, because at each time we think we're making progress, we find that we have more variety again. For example, with the 92 elements, we thought we were making some progress when we found that they were only differing in the number of electrons that there were on the outside. Each atom then is represented by a nucleus and electrons going around. The electrons from one atom are identical to the electrons from another. All that the atoms differ by is the number of electrons. Now, further studies of electrons until today have never pointed out, never shown that there's any structure inside of them at all. They seem to be very elementary, what we call elementary particles. They have very simple properties. Well, simple from our point of view. It's mathematically simple, but hard for us to understand. They have simple properties, or let's say well understood, well described, completely describable properties. But the little core around which the electrons go, the nucleus of the atom, turned out not to be so simple. First, I better tell you what I mean by little before I go any further. I forgot. The atoms are very small. They're so small that if an apple was the size of the Earth, the atoms in the apple would be about the size of an apple. The atom now consists, if we magnify it to about the size of a room, we have the electrons going around, and we'll find in that little core in the middle is no bigger than a piece of dust in the size of the room. And in that piece of dust is contained almost all the weight of the atom. The electrons are very light and fly around it, attracted by electrical interaction with the nucleus. Now, we have a variety. The question is how many electrons gather around each nucleus. It turns out that the nuclei contain different amounts of what we call electrical charge. Some contain 6 positive charges, some contain 8 positive charges. The ones that contain 6 positive charges will gather 6 electrons and it'll become a carbon atom. The nuclei that have 8 positive charges will gather 8 electrons around them. But all the nuclei of carbon atoms turned out not to be the same. Some were heavier than others. They all both had 6 charges, but they weren't the same weight. So these different weight nuclei were called isotopes. So you see, we had more different kinds of nuclei then we had different kinds of atoms, because each atom had a number of different nuclei. So suddenly the variety increased again. The nuclei exploded into hundreds of varieties of different weights and different charges. But again, we were able to make from this variety certain simplicity. It turned out that we could understand the nucleus if we imagine that they're made out of two kinds of particles only, called a proton and a neutron. The proton and a neutron have about the same weight, which I'll call it a unit of weight. This is just rough. And the proton carried a positive charge, but the neutron was neutral. So we might have a nucleus like containing 6 protons and 6 neutrons. This would be carbon, because the protons carrying the 6 charges would attract the electrons, making 6 electrons, and that makes the atom chemically like carbon. The weight of it would be about 12 units. Or we could have a nucleus with 6 protons and 7 neutrons. Because it had 6 protons, it would still attract 6 electrons. Again, it would be chemically carbon, but instead of a weight of 12, it would be a weight of 13. Having 6 protons and 7 neutrons is 13 units of weight. So that the isotopes were explained by different numbers of neutrons, and the variety of chemical was explained by the number of protons. So the atoms were nothing but numbers. Numbers of very simple objects.
So how many particles do we have now?
We have light, which comes in a particle too, called a photon. We have electrons, and we have protons and neutrons. And that explains all about the nucleon. So it seemed again that we had things reduced to a very simple level. And I tell you today, we have never analyzed light any further. Every property that it has can be understood from a simple photon, and we've never found any complication on the outside of the atom in the electron. But when it comes to a proton and a neutron, aha, the plot thickens again. The problem starts when we try to figure out what holds the protons and neutrons together in a little nucleus instead of letting them fly apart. I disregarded some things when I was talking before. First of all, what holds the galaxies together? That's gravitation. I left that out when I was listing the elements of the world. We have the force of gravitation is one. Then, what holds the electrons to the nuclei in an atom? That's the electrical force. I mentioned that before when I talked about light. Then, what holds the protons and neutrons together inside a nucleus? That is a mystery that we're started out to try to solve. And one way to try to solve these things is to find out what kinds of forces there are between particles, is to hit them together and see how they bounce away from each other. By seeing how they bounce away from each other, we find out what kinds of forces, what kinds of pushes and pulls there are between them.
How do you do this experiment?
And the way we do an experiment like this is we take a proton, and we can get a single proton because that's just the atom, the nucleus of the atom of hydrogen, of the lightest form of hydrogen of weight 1. There is a hydrogen of weight 2, which has 1 proton and 1 neutron in it, but most atoms of hydrogen are hydrogen of weight 1, which consists of just 1 proton and 1 electron. Now we knock the electron off with electrical forces, and we have just the proton, and accelerate it, make it go faster and faster by pulling it electrically. When it gets going faster and faster and faster, we let it plow in to a piece of matter. And most of the time, it just misses. It rips through and leaves a lot of trail of torn up atoms behind, and it doesn't hit a nucleus. That is, it doesn't hit another proton or neutron because the nucleus is so small. But once in a while, it does. And the nuclear collision research is what we have to study, what we try to use, these rare collisions in which a proton hits a nucleus. When the proton hits the nucleus, at low energies, all it does is knock protons or pieces or little groups of protons and neutrons or other partial nuclei out of the nucleus. In other words, it just splatters the protons and neutrons. In order to find more out about it, though, we have to make the experiments at higher energy. All we'll find out about that is that how the nucleus is put together. We want to go further and find out about the proton. When we have hit the collision a little harder, we find that the forces are very complicated. There's nothing as so simple as the electrical forces. The protons seem to be a more complicated device. And we discover new particles are being knocked out. As the energy rises, we discover that when we hit protons against other protons, for example, that we get not just two protons out at some angle, which is what we might have expected, but we also get other particles. Some of them are called pions, some of them are called sigmas or k-mesons, and so forth. We find a great variety of particles coming out. Many of these particles have to be inferred. That is, they're so unstable, they disintegrate right away in a very, very tiny time, and so we have to deduce their existence. But at any rate, at very high energy, the plan that we had, we thought we were near the end, the plan that we had of hitting protons against protons or protons against neutrons to find out what their structure was, broke down. It's like this. Suppose we wanted to find out how a proton is like a watch perhaps, how it's made. Then we hit two watches together at high speed and gear wheels should fly out. That would be all right with watches, but the trouble is that the laws of matter are a little bit different. The particles that come out weren't in there. The particles are created from the energy of the collision. So when we hit a proton and a neutron together with the new machines, with hundreds of billions of electron volts, that's a unit of energy, with the highest energies that we can make, we make many, many particles. We make a great variety of particles. There may be, for example, in a particular collision, maybe 12 particles come out. But the 12 particles weren't in there. And now the new problem is to decipher what it all means. What I mean when I say 12 particles comes out is not that just exactly 12 come out. Sometimes when we hit the two together, we get more and sometimes less. And of these 12 particles, some of them are identical to each other in character. But there are different kinds of particles that come out, not just 12 different kinds, but sometimes in rare collisions, special kinds come out, sometimes more often. And it's very hard to tell what the number of different kinds of particles come out, because every day we're discovering new ones. You might say in several hundred, say 400 at the present time, of different types of objects that have been created by colliding neutrons and protons together. So again, when we thought we were near the end with a simple variety, to get the nuclei, which had large variety, into small number of objects, neutrons and protons, stuck together with a mysterious force, in analyzing this, we find indeed that there aren't just those particles, but several hundreds, again, of a great variety of different kinds of things. And so the next question is whether this variety can be understood, again, as all these different types of particles might be perhaps understood as being made of some other thing. Now we have a theory at the present time. Well, the first thing that we did in order to try and find out about this is analogous to what Mendeleev did, is to put the different elements in charts to notice that there's certain relationships, that some elements behave very much like others, and that there's some kind of periodicity if you arrange them according to their masses, and there was some regularity of the chemical elements. So what we do is we arrange them according to their masses and other properties, electrical charges carried by these 400 or other particles, different variety of particles. We find a number of numbers that we can use, which we call quantum numbers, in order to describe the various particles and put them to see relations among them. In other words, to make a kind of Mendeleev chart. We've been rather successful with making a system of pigeonholes in which the particles appear to go. They appear to be in families of various kinds. There are groups, for example, of 8 in a certain pattern. And that pattern of 8 is repeated again and again at different spins, or different, that is to say, degree to which they're rotating around their axis. It's called a spin. At different masses, we find the same pattern of 8 repeated. There's another pattern of 10 in a kind of triangle of masses. And this pattern is repeated again and again. Also, we found that the particles can be separated, first of all, into two mighty classes. One is called baryons, and the other is called mesons. We distinguish them this way. All the particles are unstable. They disintegrate until they get to the one of lowest mass, and the one of lowest mass is a proton. So if they ultimately disintegrate into a proton, they're called a baryon. If when they ultimately disintegrate, they end up as nothing but light, no proton left over, they're called mesons. So we have these two great classes, baryons and mesons. Then we have pigeonholes for baryons and pigeonholes for mesons. Now we've cooked up a theory. We have a little idea. It turns out that the character of the pigeonholes could be understood if all of these particles, both baryons and mesons, are made out of little particles called quarks. And the baryon should be made of 3 quarks, and the meson's made of a quark and an antiquark. I haven't talked about antiparticles, but an antiparticle is one which has exactly the opposite properties. For example, if an electron has a negative charge, the anti-electron, which is called a positron, has a positive charge. And a particle and the antiparticle can annihilate with each other. They can come together and simply disappear into energy in the form, for example, of light. Or in reverse, particle and its antiparticle can be made as a pair from just the kinetic energy of collision of 2 other particles. That's why we get such a big variety of different things made in a collision between an energetic particle and another. At any rate, to get back, a meson is made of a quark and an antiquark, and a baryon is made of 3 quarks.
How many different types of quarks are there?
Only 3. There's 3 kinds of quarks which we've given the interesting names of the up quark, the down quark, and the strange quark. I have a little trio of bongo players. We like to play drums together, I and my 2 friends. And we call ourselves the 3 quarks. One guy is tall, one guy is short, and so they call them up, down, and strange. I'm strange. But with these 3 varieties, the different kinds of baryons can be understood this way. For example, you can make a baryon of 2 up quarks and a down quark, or one of 2 down quarks and an up quark, or one of 3 strange quarks, and so on. Now, if you think a while, you find that doesn't make a very great number. If you think a while, you'll find that there's just 10 ways of arranging 3 quarks together, each one of which can be either up, down, or strange. In fact, that 10 is the secret behind that little group of 10 in the pattern that I tried to describe before. But the next feature that we recognize is that the quarks don't have to just sit next to each other, but they can move in different ways. In other words, the quarks are held together somehow, and they vibrate among themselves, and in vibrating in different ways, they have different energies, they have different states of motion. And these different states of motion, they appear to be these different particles, these 400 different, well, not so many, the baryons, which are maybe 200, different baryons, are systems of 3 different quarks moving in different kinds of patterns. And when you count up what kinds of particles you will get, what families of particles you can get from different types of motion, you'll find a system of pigeonholes, a system of possibilities, which are just exactly fitted very well by the periodic chart that we had laid out before we had made up the theory of quarks.
Can you characterize these quarks somehow with analogies or...
These quarks have to have certain properties, of course, to get the right properties for the protons and neutrons and so on. And I'd like to tell you what one of them is. They carry electrical charge. The up quark carries a charge of plus 2/3. The down quark and the strange quark each carry a charge of minus 1/3. Now, we have never seen in nature any particles which carry a charge of 1/3 of a unit or 2/3 of a unit. But we need these charges to get the right answer. For example, if a proton is made of 2 up quarks, and a down quark, each up quark has a charge of plus 2/3, and the down quark has a charge of minus 1/3. So 2 plus 2/3 and 1 minus 1/3 is 4/3 minus 1/3, or 3/3, which is 1. So the proton has a charge of plus 1. Neutron is 2 down quarks and an up quark. It has therefore a charge of minus 1/3 from each down quark. That's 2 times minus 1/3, or minus 2/3, and plus 2/3 from the up quark, and so it balances out. It has no charge. Isn't it clever? By putting 3 objects together, each with these 1/3 unit of charges, we get integral charges. It's very amusing indeed. The mysterious thing is that we've never seen any objects with one-third charges, so it's a matter of imagination. The easy way to find out whether there are quarks or not, and whether this theory is right, if the theory was right, we would expect that if a quark is, for example, made of two ups and a down quark, and if we hit two protons together hard enough, we'd knock the quarks out. Then we'd find the loose quarks, the up quark or the down quark. If we did, we would find a particle in nature which had a charge of 2/3 or minus 1/3.
How can you check the electrical charge that the particle carries?
It's very easy. As it moves along, very energetically, nearly at the speed of light, through matter, it tears up the atoms in the neighborhood because of its electrical effects. But if the electrical effects are only 1/3 as great, it tears up, as it turns out, the square, 1/9 as many atoms. And thus there is not as strong a track left in some of our instruments, by a factor of 9. And that would be very easy to notice, that we'd get a track that was 9 times weaker than the response that we would get from an ordinary particle, like a proton. Well, people have been looking for quarks this way, to look for tracks in cloud chambers, or sparks in spark chambers, or some kind of an effects, electrical effects, that would show that atoms are torn up by an atom particle going through, but a particle of 1/9, or 1/3 the charge, or 2/3 the charge. That is to 1/9 or 4/9 the strength of an ordinary particle, and it's never been seen. So we have a little puzzle, because we have an object which is made of quarks. Is a nice thing to explain the pattern, but the experiments don't show that the quarks come apart.
But the solution?
And one possibility is the quarks are held together by tremendous forces. But if they do that, then they're moving around inside these things at very high speed. And we know enough about the theory of relativity to know that the situation can't be very simple when they're moving at very high speed. There should be pairs of other quarks and anti-quarks made in those situations. We cannot make a simple model with the periodic properties that they have unless we imagine the quarks are moving around inside relatively slowly. If they're moving around relatively slowly, they're not held together very strongly, and so they should be made. You see, the experiment would indicate that there are no quarks. We can't make them. But the pattern is so beautifully fitted by the idea that there are quarks that we are standing at the threshold of some sort of paradox. The things behave exactly as if they're made out of quarks, with the single exception that they don't come apart. Now, faced with such a paradox, some people say the whole idea that they're made out of quarks is not right, and that the fact that the pattern fits is due to some deeper significance and has to be understood mathematically in some other way. There are others who say, well, it's true, the quarks are held together in some way by new kinds of forces that we don't understand. They can't really come apart for a reason that we'll discover later. And we can philosophize about this all we want, but in science we have the advantage, and we can always do some more experiments to find out more. So the next thing that we're going to do, with an electron against a proton, we don't understand the target, but at least we understand the beam, so it's a little easier to analyze. Now, by colliding electrons against protons, we get a chance to see the behavior of the things that are inside. There would be two possibilities, for example. It may be that the proton is some kind of a smooth, like jellyish stuff. Or, on the other hand, it may be made out of internal parts, little point-like particles that are moving about. Now, what happens when an electron hits a little hard point-like particle, and what happens when it goes past electrical jelly, is entirely different. And the result, the picture of the quarks would be that there would be little hard particles inside, whereas some other pictures may not agree with that. Well, when we bounce electrons against protons, we find that the proton behaves as if it's made out of little granular particles moving around inside. It doesn't turn out to look like it's exactly 3, but we understand the reason for the number not being right. Are these particles quarks? Or maybe the proton is made out of some other particles different than quarks. The first thing that we can measure is what we call the spin of these particles. The quarks are supposed to have a spin like that of an electron, which is called spin 1/2 of a unit. And when we scatter the electrons from these particles, we can tell by the probability of the electrons being scattered at different angles what the spin is of the little parts that they're bounced off of. And lo, the spin is a half. So we now know that the proton is made out of little parts, or perhaps it is at least, made out of little parts of spin 1/2. Now can we tell what the charges of these things are? And the answer is that by scattering electrons, we cannot. We can just tell something about their momentum distribution, the speed distribution that they have inside. We cannot tell what charges they carry. We can tell, though, that if the charges were 2/3 and 1/3 and 1/3, as we said before, that the total amount of momentum that a proton carries is not correctly given by the quarks. In fact, it shows that there must be something else inside that the electrons do not bounce off of. Now, electrons bounce off of anything that's charged. It doesn't bounce off of things that are neutral. And so we would conclude, if the quark theory is right, that the quarks have spin 1/2, but there's something else neutral inside the proton. Now that's not so bad, because the question would ordinarily be, if you said that the thing was made out of quarks, what holds the quarks together? It must be something strong, because if the quarks are held together so hard or in such a mysterious manner that when you hit protons together, the quarks don't come apart, something's holding them together. So we have a new particle to hold the quarks together. This object we call a gluon, horrible word, after the glue which is holding the quarks together. But anyhow, at any rate, our experiment shows that if the particles that are inside the proton are quarks, there indeed must be something else in addition. Now the really challenging question is whether the quarks carry charge 1/3 when they're inside the nucleus. And this looking with electrons will in principle measure the charge, because the ease with which an electron is bounced back from a particle, a quark say, depends on the charge on the quark. But since we have no independent way to know how many quarks are in there, we can't tell for any particular direct way whether the charges are indeed given by 1/3 or 2/3. If we had some other way of bouncing something off a quark that wouldn't depend in a different way on the charge or how many quarks are there, it would not depend on the charge, but it would depend only on how many quarks are there, we would have a chance of seeing whether the electrical scattering was indeed given by 1/3 and 2/3 charges. Well, we do have a way, and I'll jump ahead of a story a little bit to tell you there's another particle, a neutrino, that I'll come back to, that we can use to scatter off the quarks. And so we've planned an experiment in which neutrinos are to be scattered from protons in a way analogous to the way electrons are scattered from protons. And when we find the probabilities of scattering of neutrinos from protons, we will be able to tell whether the quarks are really showing their non-integral charges, their 1/3 and 2/3 charges in the electrical experiment or not. This experiment with the neutrinos is set up for example, in several places. One place is a National Accelerator Laboratory in Batavia, the United States. And the beam is turned on, and probably as I'm talking now, the neutrinos are coursing through the apparatus. We have to get a large number of collisions and average the collisions, and I wish I knew the results at the present time. This will make or break the quark picture of the insides of a proton.
Could you tell more about these experiments?
If you'd like, I can tell you a little bit more about how these experiments of bouncing electrons off of protons tell us what the proton looks like. When we do this, the first experiments that did this just looked at the average proton, and it looked like just a cloud, a small cloud. The question is whether this cloud is a kind of jelly or is made like a swarm of bees, of small hard particles moving around. Now, another way to tell whether a thing is made of a swarm of bees would be something like bouncing radar off. You know, by radar we can tell the speed of an automobile by the way that the waves that bounce back are changed when they're bounced from a moving car. So if we shine radar waves at a swarm of bees, the waves that come back can show that there are particles inside moving about and measure their velocities. In the same way, when we scatter electrons from a proton, if we measure the speeds or the momenta of the electrons that are bounced back, they reflect the distribution of momenta of pieces inside the proton. And so it's this experiment that we've done to watch the distribution of electrons, which have been a distribution of momentum of electrons that have been bounced back from a proton, to determine what the momenta are of the pieces inside. And what we've discovered is indeed there are pieces inside and that they're moving about.
What do you contribute to this research?
And it's very hard to say, because a program like this is developed by large numbers of different people over many, many years, and I made minor contributions here and there. Perhaps one that's more relevant to what we've been talking about is I think it was I contributed to the idea that the observations of the distribution of electrons from the scattering from a proton can be interpreted as the moving about of hard, small particles. In other words, that we can interpret the experiments of scattering electrons from protons as indicating that the proton is made of small, moving particles.
What kinds of machines do you use for the experiments? What do they look like?
In an ordinary electron microscope, the electrons pick up their speed in going through a little gap of about an inch. Here we need, to look at such a tiny object as a proton, very much more energetic electrons by several million times. And so we need an accelerator to accelerate the electrons to high speed, which instead of being an inch long is more like 3 kilometers. So we have this long tube of 3 kilometers at the Stanford University. And at the other end, there are several big buildings that contain the apparatus, which is very enormous for measuring the electrons which are scattered from the proton. The machine which is used to generate the neutrinos is also extremely large. It consists of a big circle at Batavia in New York. It consists of a big circle of about 6 kilometers in circumference in which protons are accelerated. The protons hit a target and they make new particles, one of the particles I mentioned earlier, of the 400 varieties, called pions, and they disintegrate, ultimately producing neutrinos. And the neutrinos are then used to produce reactions in further matter further down the beam. The targets for the experiment is about 3 kilometers from the machine.
Does the hypothesis of the quark explain everything about the nature of matter? Is the quark the smallest building block?
We find that matter is made out of atoms, and atoms are made out of electricity, and electrons and nuclei are made out of protons and neutrons are made out of something, perhaps quarks. Maybe we'll find out what quarks are made out of, and we'll have a never-ending search. Maybe there's no final answer. I think that for people who think that it's necessary to have the complete answer to do any research, that the purpose is to find the complete answer, that looks like a complete discouragement. But the idea is not to find necessarily to find a complete answer, but to find out more and more information. It's like exploring. If you were exploring a country, the fact that when you went through the country, it may be that on the other side you come across a ocean that you'd have to pass and you couldn't pass, doesn't mean that it wouldn't be interesting to explore the new country that you discovered. So in the same way, the question as to whether this is a never-ending search or that the search will end with the quark is not exactly relevant to our interest in finding out just more about the way matter is constructed.
Is this study purely theoretical, or can we use it somehow for our technology, practically?
In all the past discoveries about the properties of matter, we've found enormous practical applications of our new knowledge. The new knowledge of matter meant that we can control matter and make it do things that we want it to do. And you may ask whether we expect to have practical applications from these developments too. A man would be a fool to say there are no practical applications, because it always turns out as soon as you say that, in a few years there are. But actually I can see none. In the other cases when the laws were being unfolded, it was almost obvious that they would have some application. But in this particular case, I can see no particular practical places where much of this will be of great use. This is, however, man's curiosity, which leads him on to discover more and more about the world. The fact that there are practical applications doesn't stop that, or there aren't, doesn't stop that curiosity. And so it's something like the way we study astronomy. The exact position of the stars and the galaxies and the universe, the size of the universe and these mysterious things have no practical application. It's true that astronomy can be used for navigation, or it used to be used. It's very rarely used now. Furthermore, the amount of astronomy you need to do practical navigation is minimal. But the tremendous interest in astronomy shows our interest in the universe we are in, to find out what we are, what the matter is made out of, and so on. And this search for the insides of a proton is analogous to the search for the outside galaxy.
What is the role of theoreticians in science?
Well, it turns out that the problems to understand nature is very difficult. It's very subtle, and it takes a lot of imagination to try to imagine what it could be like in such a way that it has to agree exactly with the way she actually behaves. We need a kind of imagination in a straitjacket. We have to imagine what's there. If we imagine something that isn't there, it isn't going to do us any good. And it's so difficult and subtle that it's turned out that there's a kind of division of labor. There are people that spend almost all their time thinking about just those problems. And those are called theoretical physicists. There are others who do a good deal of their time they spend in thinking about these things, but also in doing experiments to gather new clues and new tests of the imaginations of either themselves or others. Those are called experimenters. I don't mean to imply that experimenters don't think and don't have imagination. This division is only a system of words. The experimenters also do a great deal of imagining, and their being closer to the actual phenomena very often suggest clues as to how the thing actually might work. But some of the more subtle and difficult questions are analyzed by people who have spent their entire time on this problem, and they're specialists, you might say, in thinking about physics, and those are theoretical physicists. That's what I am. That's, for example, what Einstein was. People have called him a mathematician, but that was in a day when they didn't know what a physicist was. He was a theoretical physicist. I should like to mention one other curiosity about the way the quarks have to behave. We have discovered a principle when studying atoms that's called the exclusion principle. It says that no two electrons can be in the same state, and we think we have proved that for spin-and-a-half objects there must be a rule that no two can be in the same state. Nevertheless, in making our picture of the quark model, we have to make the exact opposite hypothesis, that the particles like to be in the same state, that the energy is lower and the conditions are enhanced when all the particles are in the same state. We think we proved that this is impossible, but in part of the proof it was assumed that the particles can be separated from other particles. Now we know experimentally the quarks have not been separated, so it's still possible that the things obey a different rule, that they like to be in the same state instead of try to avoid being in the same state. But this again adds to some of the paradoxes associated with our picture that protons are made out of quarks. It's these paradoxes that makes the whole subject very interesting, because we're bound to learn something new. We learn a paradox in physics of this kind is generated because we have a set of ideas that we think are all necessary, and nature doesn't pay attention to one or two of them. And the question is, which one? The paradoxes are the beginnings of inklings that we're about to make progress in overturning some of our ideas. Of course, I can't tell you which idea we're going to overturn. People who are more conservative have proposed a more complicated picture, that the quark, because the rule is that no two particles can occupy exactly the same state, and yet three quarks tend to do so in some of these particles, they propose that maybe the quarks, which seem to be the same, are really different. Their theory is that the quarks come in three colors. For example, there are three kinds of up quarks: red, blue, and white. Then the quarks that are in a proton has one red, one white, and one blue, so that none of them are in the same condition. Also, in order for this theory to work satisfactorily and to account for everything, the glue has to have color. It turns out 8 colors. So now we've got our theories really expanded in this view. We have each quark has 3 varieties, up, down, and strange. And each variety has 3 colors, red, white, and blue. So we have 9 different quarks and 8 different gluons. There's 17 particles. And we haven't mentioned the graviton, photon, and the 4 leptons that I mentioned earlier. So we have to add another 6 particles up to 23. And though it's far from our subject, there are suggestions for other particles, too. So we perhaps have 24 particles at this stage. So it looks like the simplicity is turning into variety again, even before we're sure that the quarks exist.